Hi there, my name is Finian McCann from London University. I'm going to present some research that we've done on the fire performance of high-strength steel tubular connections. So the motivation was that during fire events, when there's a loss of stiffness around a frame, in a connection that's been designed as partially rigid or rigid, and therefore attracting moment at room temperature, as it loses stiffness, we might see just a redistribution of moment throughout the frame, which might lead to stress concentrations arising elsewhere in the frame that hadn't been expected in the original room temperature design. So for example, where we might expect plasticity within the connection, that might actually shift towards larger deformation instabilities occurring elsewhere in the frame. And this might have implications for progressive collapse. So via a combination of experimental and numerical analyses, we want to investigate such shifts in failure mode in high-strength steel connections with increasing temperature. So we start off with some tensile testing from some square hollow section S460 sections, and we derived some average properties for yield strength, ultimate strength, and modulus of elasticity, which are then used to calibrate a numerical model later on. The tests were done on 5 connection assemblies comprising 2 stubs, so a beam stub and a column stub, which the beam stub was welded to an end plate, and that end plate was then bolted with 4 bolts into the flange of what we call the column stub. It was inclined to 45 degrees to assist installation in our rig, and then also to simulate combined bending and axial thrust. We had a bespoke hinge fabricated by our workshop to provide pin-ending conditions at the top, and then we had a roller underneath the base of the column stub down below. So this is what it looked like in the lab itself. This is actually after one of the tests. So you can see our hinges. We applied the temperature via ceramic heating pads, which were controlled by an inverter informed by thermocouples. We put an LVDT at the roller, and then, as you'd expect, we had an internal load cell and displacement transducer within the 500 kilonewton jack itself. This is then all wrapped in insulating material, which has been exposed in the picture here. So it's done in 2 phases. The first phase was a heating phase, which brought up to a nominal temperature. So this is the control thermocouples for the ceramic heating pads. And these nominal temperatures were room temperature, 150, 350, 550, and 750 degrees C. Okay, so 7 to 8 degrees per minute up to the set point, and then held roughly constant, approximately constant, for the loading phase of the test. If you're looking at then load displacement curves, so we have overall trends of, as we'd expect, decreasing strength, decreasing stiffness, and increasing ductility as the temperature was increased. Just know that the 20 degrees C, the room temperature test, unfortunately the data logger failed halfway through, but it was a full and complete test, which we can compare in terms of failure modes later on. So as you see here, 20 degrees C and 150 degrees C all the way up to 550 degrees C, we had connection failure. Okay, so we had the failure mode involving prying of these tension bolts and then buckling and bending of the end plate. However, at 750 degrees C, so the highest temperature we tested, we see a change in failure mode where the connection maintains its integrity, and then we see plastic hinges, or certainly an excessive rotation occurring within the stubs, as highlighted here. Okay, so plastic hinge really forming in the beam stub there, with some rotation in the column stub as well. Now, of course, these are where the ceramic heating pads were applied, and therefore there'd be a concentration of heat. So, we might say that this would be naturally expected. But it is worth noting that, of course, we didn't see these kind of rotations within at the lower temperatures. Okay, so it's mainly attributable to the location of the ceramic heating pads, and for that particular test, the temperature at the connection was around 520 degrees C. But there are similar temperature differentials present in the other specimens, and yet failure initiated at the connections, which were always, slightly cooler. So what we can say is, for a variety of kind of interacting reasons, there is increased temperature leading to a mode change. Okay. And just to show here, we got Eurocode strength and stiffness reduction factors plotted against temperature. And so this is 750 degrees C would have been the temperature in the beam stub and the column stub. 520 would have been the temperature in the connection of that specimen. But there was also a similar differential between the 550 degree specimen, the temperature in the beam stub, and the temperature of the connection was 370. Okay, so the relative loss of stiffness has changed the type of failure mode that we expect, even though there is a similar temperature differential. So with the experiments done, we then moved over to finite element modeling. Okay, so we created a solid element model in Abacus, which is a combination of hex elements and tetrahedral elements. So mainly hex elements for the hollow sections and the plates. We increased the mesh density in the neighborhood of the connection. We had pin conditions at the hinge, and we also applied measured lateral displacements applied to the base. And here you see the increased mesh density around the connection. In order to model the behavior at the joint, we used friction contact, hard contact, so tangential behavior of divided by 0.3, and that was applied between the end, the bottom of the end plate and the top of the column flange, and then also between the undersides of the bolts and the top of that end plate. Now, in order to aid convergence, what we found was it was better to actually replace the contact definitions on the underside of the column flange on the inside with a tie constraint. And what the kind of rationale here is we were looking at how the deformation mode was happening in the experiments, and then modeling and then using a bit of kind of rationale to say that these surfaces never separated. And we can see it again in the failure modes later on. We'd expect maybe some kind of slip up at the top here, especially with these prying connections and with these pried bolts. So we found that we didn't lose any accuracy, but we definitely aided convergence by changing these from contact definitions to tie constraints. So it's just kind of a useful kind of finding from our numerical analysis. In terms of material modeling, so the room temperature material properties, FY, FU, and E, were taken from our coupon tests. And then the elevated temperature properties were determined by applying reduction factors from the literature, and then these reduced material properties were used to calibrate Ramberg-Osgood models defined by Fang and Chan in 2018. So this is then a summary of the stress strain curves. It's noted, of course, that we're using an oral model for the room temperature results, which we did see a well-defined yield point, but in the end the results worked out. There was a good agreement observed between the experimental and numerical results. So that was for the S460 material. For the class 8.8 bolts, we just used the reduction factors from Eurocode 3 with a bilinear material model. So linear strain hardening from the yield point up to the ultimate stress. So then we had to move on to, now they've got the material properties sorted, how do we then apply the temperature profiles, the temperature distributions? So instead of modeling the entire geometry and doing a thermal analysis in Abacus, decided just to try out using a quadratic polynomial fit. So using let's say the distance along the beam stub and the distance along the column stub as the ordinate, we used a quadratic fit through the experimentally recorded thermocouple temperatures. Okay, so we ended up with these quadratic fits along here, and this is based on previous work that I've done in hot pipelines, so offshore pipelines. When we heat them up, we tried out putting in polynomial fits, and the results came back to be quite good. So we took that rationale again and applied it in the current analysis. Okay, so now just then comparing the experimental curves and numerical curves. As I said previously, unfortunately for the room temperature test, the experimental curve cut out early, but we can see that the initial linear stiffness is very, very close. And that's the same again for the 150 degrees C. 250 degrees C, a linear stiffness, very close agreement. Some disagreement there with the actual strength, but at least we are on the conservative side. For 550 degrees C, we have very good agreement across the whole displacement range. And then for 750 degrees C, we found that there was an overestimation of the strength for 750 degrees C. So that's something that we need to kind of look at again in closer detail. But again, the initial linear stiffness still looking very good. And if we're comparing failure modes, again, we see that for the 20 degrees C, 150 degrees C, 350 degrees C, and 550 degrees C, there's close agreement, very, very kind of a good representation of the failure modes that were occurring within the connections. And again, it's worth mentioning that just like what we saw in the experiments, the numerical analyses all showed failure occurring within the connection. And most notably, when we move to 750 degrees C, so the hottest temperatures, again, because of the elevated temperature occurring within the beam stub here, we found the maximum rotation occurring there. Okay, so we had let's say a numerical, we had agreement between the numerical and experimental models that this shift of mode was also occurring as we increased the temperatures. So in summary then, we had 5 partially rigid connections fabricated and tested in combined bending and axial thrust at various temperatures up to 750 degrees C. We had overall trends of decreasing strength, decreasing stiffness, and increasing ductility, as we would expect with increasing temperature. We had good agreement between a numerical finite element model and the experimental results. We found that these quadratic fit temperature distributions approximated the actual temperature profiles quite well and led to good agreement in the numerical model. Therefore, lending credence that we can avoid, or we can certainly kind of reduce the amount of thermal modeling that might need to be done. Strategic use of tie constraints rather than full contact definitions in bolted connections can aid convergence without compromising accuracy. Just the main thing there is you need to just consider what surfaces are going to remain fastened together and what surfaces might slip or might separate during deformation. And the main kind of output here was that failure at lower temperatures occurred in the connection, while at higher temperatures failure occurred away from the connection. So there's a temperature effect occurring here that's shifting the failure modes away from what we would have assumed at room temperature. So thank you, folks. That's the end of the presentation. Willing to take any questions, and a final note of acknowledgements to Imperial College London, who very gratefully supplied the material.